Previous work has shown how high-quality depth estimation can be obtained from a stream of posed RGB frames, and the utility this kind of model has for online low-latency reconstruction and AR effects. The basic bedrock of such models often incorporates plane sweep stereo to build a cost volume, followed by cost volume regularization using 3D or 2D networks with a learned monocular prior. 3D reconstruction is achieved through cheap TSDF fusion. There are, however, limitations. The learned monocular branch does its best to recover a complete metrically accurate depth map from the noisy cost volume, but it can only do so much. Source views rarely cover the entire field of view of the current frame, leading to missing likelihood estimates for depth that the rest of the network has to recover from. Textureless regions also pose a challenge for visual feature matching. Errors from such lapses may be small, or they may be catastrophic, leading to a completely incorrect metric estimate. While adding source views to the cost volume improves matching, there is a point of diminishing returns, beyond which adding source views increases computational burden, without improving accuracy. In existing architectures, for every new frame, a cost volume is made and regularized. On the next frame, this depth prediction is forgotten about, and a new metric estimate is formed via plane sweep in the cost volume. While the network's cleanup of the cost volume isn't perfect, and so nor is one depth frame, perhaps a group of them together, averaged, are. Hash TSDF fusion already provides a computationally inexpensive way of aggregating multiple depth estimates into global geometry that's then easily accessible via marching cubes as a mesh. What if we could use this cheaply available global geometry we've built so far as part of our current depth prediction? We call the depth render we get from rendering the live mesh a geometry hint. This geometry hint is cheap to compute, and we include it right after the matching step in our cost volume, aggregating it with the plane sweep matching score using hint MLP. However, since the mesh is still under construction, certain parts of it may not be reliable quite yet, and require more aggregation before becoming useful. To account for the reliability of still under construction live meshes, we utilize standard TSDF confidence measures to inform our network of how reliable the rendered mesh is. We visualize the confidence here as a heat map on the mesh and as a 2D map rendered from the point of view of the camera. Our hint MLP now also takes in the sample TSDF confidence value for every pixel. This geometry hint and confidence map are optional and are passed to the network on every new current frame if available. We call this hours incremental. On every step, we render the geometry hint and sample the confidence from the TSDF and pass those to the network, producing a depth prediction, fusing that into the TSDF, then repeating the process. Our new model yields a new state-of-the-art for online depth estimation on ScanNet v2, while remaining fast at interactive speeds. Please see the paper for complete scores. The model also achieves a new state-of-the-art for online 3D reconstruction. When looking at the winner-takes-all estimates from the cost volume side by side, it is clear why our model outperforms the baseline. Utilizing the aggregated global geometry of previous predictions allows the model to achieve a much better metric estimate given a much less noisy cost volume. Our model is flexible and can also be used for offline depth estimation and reconstruction. We run the model once to produce a hint mesh, then run it again, using renders of the hint mesh for new predictions. This yields a new state-of-the-art for offline feed-forward reconstruction, taking an average of 13.8 seconds on the ScanNet v2 test set. Our model can also be used in cases where a mesh is available from a previous visit to a location. We show that our model is robust to scene changes, relocalization errors, and pose noise, outperforming the baseline. Overall, our model shows superior metric depth performance. Those depths yield sharper, more complete reconstructions. This advantage holds for both the online and offline cases. We also show how our model performs well in the reconstruction of out-of-training distribution scenes. While our training data doesn't contain moving objects, the model still performs well in their presence, rejecting low-confidence global geometry as a result of transient objects. Thank you for watching.